Previously, we've looked at the problem of finding relative minimums and maximums of functions of two variables. The first derivative part extends to any number of variables, but the second derivative doesn't. In this video, I want to talk about how we deal with the situation where we're looking for absolute maximums and minimums. The situation is more complicated than it was in Calc 1. In the first semester, we saw that you could have absolute maximums and minimums at the endpoints. So the function values there are candidates for biggest and smallest overall function value. We also saw that if you're between a and b, if you can find places where the first derivative is 0 or doesn't make sense, does not exist, those are also candidates for absolute maximum and minimum values. So you just make a list of all such places, you look at the function values, the biggest one is the absolute max, the smallest one is the absolute min. The beginning and ends of this interval play a role that's different from f prime of x equals 0, or doesn't exist though. So I want to look at that in some detail. If I have a number that's strictly between a and b, then I can make a little interval centered at that number, which is completely contained within the interval from a to b. Every point in this smaller interval is a point of the bigger interval. In particular, the one in the middle is also. We didn't use this language, but we'll call such a place an interior point of the set from a to b. If I have a number that's strictly to the left of A or strictly to the right of B, like that, firstly, there is an interval centered at this spot so that no point of this smaller interval is a point of the interval from A to B. We'll call such a point an exterior point. And this again guarantees me that the point itself is not one of these points. Then looking directly at A and B, A is the center of some small interval, but no matter how small I make it, this interval contains both points of the interval from A to B and points that are not in the interval from A to B. The same can be said of the right end of the interval from A to B. A and B are not interior points. They are also not exterior points either, so we're going to call such things a boundary point. A and B are boundary points of the interval from A to B. Every interval of numbers centered at either one of those points contains both points of the interval from A to B and points that are not in that interval. In terms of our maximization and minimization, other than f prime being 0 or undefined between A and B, the only possible other places where I might have absolute maximums and minimums are the boundary points. Now imagine that you're in the two-dimensional plane and I have a region that is contained within some closed curve. There are places, such as that place, where I can find a small disk so that the entire disk is contained within region R, I'll call such a point an interior point. There are also points so that if I make a sufficiently small disk centered at the point in question, say this one, this disk contains no points of region R, we'll call such things an exterior point. And just as with the Calc 1 case, there are points where every disk centered at that point contains both points of the region R and points that are not in the region R. As before, we'll call such places boundary points. The rationale that you used in Calculus 1 pretty much goes as the same now. I might have an absolute maximum or minimum in the interior somewhere. The derivative would have to be 0 or undefined. In our new context, the derivative would be the gradient of f. Or you could have an absolute maximum and minimum somewhere on the boundary. In 2 dimensions already, this is not looking too good because in this picture, for instance, there's an infinite number of boundary points. So even in this simple case that I've drawn this picture of, there's an infinite number of boundary points, and we're going to somehow have to look at all of them, which will turn out to be kind of painful even in a simple case. If I have in Calc 1 the interval of numbers from A to B, not including the A, not including the B, then every point of that interval is an interior point. If you take analysis or topology, you'll at least initially take this to be the definition of something. If every point of a set is an interior point, you call that an open set. If I look at the interval from A to B, including the A and the B now, this is not an open set because the endpoints are not interior points. The endpoints are boundary points. So people take in analysis and topology the definition of a closed set, at least in some context, to be this. A set is closed if it contains all of its boundary points. The boundary points here are A and B. A is an actual member of this interval. B is a member of this interval. So this is what we would mean by a closed set. It contains all of its boundary points. In this context, if all of the points on the curve are actually points of the set, then we would call this a closed set. The other thing I'm going to need to know is the notion of boundedness. In 2 dimensions, a set is bounded if I can draw a circle around it. So this one is bounded because I can draw a circle around it. The corresponding fact from Calc 1 that we're going to have here is this. If I have a continuous function defined on a set which is both closed and bounded, then you have an absolute maximum and an absolute minimum. So if f is continuous on some region of the 2-dimensional plane called R, and the R is both closed and bounded in the sense that we've just mentioned, then f attains an absolute maximum value and an absolute minimum value. So our basic plan is going to be the same as before. I'm going to figure out the gradient of the thing that I'm trying to maximize or minimize. I'm going to find out, are there any places within the region where that gradient is the zero vector or undefined? If there are, that goes on my list of candidates. That won't be difficult. What usually is, though, is I have to look at each point of the boundary and see how big and small the function values get on the boundary. Once I've done that, though, I'll go down the list of function values that I got from all those candidates. The biggest one is the absolute max function value. The smallest is absolute min. It's worth mentioning that if this is true and that's true, then you get the absolute maximum and minimum. The converse, though, doesn't mean the same thing. It's possible to have a function that's not continuous every place. Maybe it isn't even defined on a closed and bounded set, but it's still possible to have such a thing that has an absolute maximum or absolute minimum. We're not going to be concerned about that, but we need to make sure we understand the logic. If that's true, and that's true, and that's true, then I guarantee you that that's true. As a simple example of this, let's look at the function f of x and y equals x squared plus y squared minus 8x minus 4y. I want to find the absolute minimum and maximum values of that function, but I'm only interested in looking at the points that are in this triangle. It's bounded by the y-axis, the x-axis, the straight line that has y-intercept 10 and x-intercept 5, and x and y should be bigger than or equal to 0, so that we're in the first quadrant. I'm going to look at the boundary first. The boundary is composed of three pieces. There's the piece across the bottom where y will be 0, and the x can be anything from 0 to 5 inclusive. The second part of the boundary is this vertical part here where x is 0 and y varies from 0 to 10. And lastly, I'm going to have part of my boundary formed by this downward sloping straight line. I'm going to look at each one of these chunks separately. First, let's look at the bottom. Y will be 0 and x will be between 0 and 5, including the 0 and the 5. If y is 0, then my function value is x squared minus 8x. So I'm thinking of trying to maximize and minimize x squared minus 8x on the interval where x goes between 0 and 5. It's possible that I could have maximums and minimums at the endpoints when x is 0 or when x is 5. That would correspond to the origin and that spot. If x is 0, x squared minus 8x is 0. The function value is 0. So I'll draw f equals 0 with a little arrow to indicate that this is one of my candidates. If x is 5, x squared minus 8x is negative 15. So this is the function value at the other end. It's still possible I might have something in the interior of that horizontal line segment, though. If I think of my function value as being x squared minus 8x. Its derivative is 2x minus 8. The derivative is 0 at x equals 4 on this horizontal line segment. When x is 4, x squared minus 8x works out to be negative 16. To look at the vertical side on the left, x will be 0 and y will vary between 0 and 10 inclusive. In this case, the function value is going to be y squared minus 4y because x is 0. On the vertical line segment, y goes from 0 to 10. That goes from this point to that point. We've already calculated the function value at the origin, so there's no need to do it again, but we have not looked at the function value here at the top. On the other hand, I might have some sort of interesting point strictly between y equals 0 and y equals 10 on the left vertical part of the boundary. So I need to look at the derivative of the function. In this context, y is the variable because x is constant at 0. In that context, the derivative is 2y minus 4, and obviously this will be 0 if y is equal to 2. Calculating the function value to be negative 4, the only remaining part of the boundary that we haven't looked at is this downward sloping diagonal line. Notice that I've already figured out the function value here and the function value there, so there's no need to do that again. What I need to do is to figure out if there's any interesting places in the interior of this downward sloping line. To do this, we're going to have to express the function values along this downward sloping line in terms of one variable, and then do as we did for the other two pieces of the boundary. Going sideways 5 units makes the y-coordinate change from 10 to 0. The slope must be negative 2. The y-intercept is 10. An equation for this downward sloping straight line is y equals 10 minus 2x. I'll express everything in terms of x and then see if anything interesting happens on this straight line between x equals 0 and x equals 5. Assuming I've done my algebra correctly, the function value, which is this quantity, simplifies down to 5x squared minus 40x plus 60. I need to know for x strictly between 0 and 5 if the derivative of this is 0 any place. It turns out that this derivative will be 0 at x equals 4, so along the downward sloping straight line, we have another candidate for a maximum or minimum. If I take x equals 4 and put it into this equation, I find out that the function value here is negative 20. We now know all about the boundary, but we haven't worried about any interior points. So that's the last thing that we have to do. Compute the gradient of the function. You'll get 2x minus 8 and 2y minus 4 for its components. If both of those were 0, 2x would have to be 8, so x would be 4, and 2y minus 4 would be 0. 2y would be 4, and y would be 2. So we have another point that is a candidate. Assuming that I've done all my arithmetic correctly, the function value at that interior point is negative 20. If I look through all these function values and look for the biggest one, it looks to be 60. 60 is the absolute maximum function value here. Also, it looks like function value equal negative 20 is the smallest one, and that happens in two different places. As you can see, even on a very simple situation, this is an extremely painful and tedious calculation. On the test, I've put in a problem like this, but nicer. If I remember correctly, you have a rectangle, so the situation isn't quite as complicated as this. So to summarize, just as in Calculus 1, we have a fairly mechanical procedure that we can follow in order to figure out absolute maximum and absolute minimum function values. But unlike what went on in Calc 1, the fact that the boundary is more complicated makes it a big mess. Coming up next, the method of Lagrange multipliers. I hope everybody's having a good day, and I'll talk to you again soon.